All right, so here we have a thermodynamics question, which I think does a really good job at forcing you to use all the concepts without doing huge numbers of calculations. Um, Although I think that a lot of the concepts are easier done with at least a little bit of the calculation, so I'm going to kind of be doing those. So we have a gas process here, and we have a PV diagram with only a couple labeled points. Right? So we have A to B. Oops, too far. Surprisingly hard to draw. Okay, one, A to B, B to C, C to D, and D back to A. Right, and we're given that in exact directions too. So A, B, C, D, and right, we go around in that nice little cycle. And our axes are not numerically labeled, but they're relative labels, I guess, right? 3, P0, P0, V0, and 4, V0, right? There. Okay. So first, we have to rank the temperatures at points A, B, C, and D from least to greatest. And so the first thing you should note is that this is going to be using the ideal gas law. Right? That's what this is really using. They all are the same number of moles, and we know something about the pressures and volumes of each point. So like, right, we know PAVA equals NRTA, or TA is N, or rather, is PAVA over NR. Right, and N and R is the same for every single gas, so I can immediately write, right, the temperature at B is PBVB over NR, etc. So all that really matters, as I can see, is that the product of these things, the bigger the products of the pressure and the volume, the higher the temperature will be. And that's all I need to really do for this. I just need to sort. I don't need calculations. So A is clearly the lowest temperature. Right? So A is the lowest. That one gets a 1. B is a 3P times V naught. Right? That's like a factor of 3, whereas D is 4 times P naught, or a factor of 4. So B has to be lower than D. And then C we see is a 4 V naught times 3 P naught, which is a factor of 12. So that one is clearly the highest temperature. And I think that even if you didn't do any calculations at all, you should immediately and obviously recognize that A is the lowest temperature, because it's closest to the origin, and C is the biggest temperature, because it's farthest from the origin. Those two you should definitely get right. It's easier to kind of mix up B and D or not know they're different without doing the calculation, but A and C are I think, pretty clear with no math at all. All right, so that's part 1. Part 2, we need to figure out the temperature at point D, and I've kind of already done it right with this calculation here. So that one, if you get part A, you've kind of probably already done, or part A1, you've probably already done part A2 at least a bit. Right, so this is at point D, it's P naught times 4 V naught, and N we actually know the number of, right? It's 3 moles, so 3, and since we're using moles, we're going to use the gas constant R. If we had that it was 3 times 10 to the 28th atoms, we would use the Boltzmann constant K, but since we got number of moles, we use the gas constant R. Right, and so this right here is a part 2. Right, so here's part 1 and there's part 2. All right, next I have to redo the gas diagram. Let's do that. So now we care about a little bit more of the details of what's happening, right? How we go from from point to point and sort of work done and energy gained and lost sorts of concepts. Okay, so work done by the gas positive. So this is important to note. And the AP sheet does define this, so there is no ambiguity, but it's easy to miss when you're reading closely. The AP sheet has this equation written about the work done by a gas. And you notice there's a negative sign here. But they give you this equation. This is the work done by the gas. So they're giving you the opposite of what this is asking for. The opposite, right, is you just flip the negative sign again. So the work on the gas is just P delta V. And this is the one you actually need to use to oops. As you can see, I flip it sometimes too. So what they give you, the equation that they specifically give you is the work done on the gas, and what you need is by the gas. You have to flip the sign. Okay? So work done by the gas. Since we want a positive work done by the gas, what we need is a pressure that's positive, that's always true, and a change in volume that is positive. So we have 4 sections, right? I've kind of drawn an arrow in each one. So in this section, the volume is not changing. Therefore, the work done by the gas is 0. That's not a positive number. Same thing with that section there. Those don't work. In the section from D to A, the volume decreases. That'd be a negative, right? That's this one. That doesn't work. And so only this one is possible, and we see the volume increases, the pressure is positive, so the work done by the gas is positive. And what I kind of explained with the equation, that's your justification. The other way you can think of it is in the sort of Physics 1 definition of work, right? Work is a force times a displacement times the cosine of the angle between them. So if the gas is pushing outward and expanding, that means it's pushing in the same direction, right? It's pushing in the same direction that it's moving in. Or theta is 0 degrees, right? Or this is a positive value. So either one of those justifications work. I think, right, this one is a little bit cleaner. Okay, so that's part B. Part C. So now we care about the process, right, going from just A to B. So that right there. From A to B, we identified in part B that no work is done. But we've also identified that in part A, the temperature has to increase as you go from A to B. So this uses the law of thermodynamics, right? We know that it's definitely true that the change in the internal energy, or the delta E, is the work that's done on it plus the heat added to it. Delta E, right, this must increase because the temperature has gone up. This is 0. So, what does the heat have to be? Well, it has to be positive, right? That's the only way you can get an increase in energy with doing no work, is heat has to be added. So in process AB, you have to check positive and then justify it with something about that thermodynamics. And whether you go back and reference some of the work concepts to show that it's 0, anything like that is useful, but not definitely required. You definitely have to state the thermodynamics laws, though. Okay, so part D. Now, you notice again they've underlined this. Now instead of talking about, like in part B, the work done by the gas, part D they're asking about the net work done on the gas. So, we have to go back to, right, that expression. And so, right, all we have to do is add up all the works in the individual parts. So negative P, actually, let's skip it. So this is work from A to B plus the work from B to C plus the work from C to D plus the work from D back to A, right? Add up the work from each of those processes, that's the net work. And some of these are pretty fast, as we've discussed in part B. So from A to B, no work is done. From C to D, no work is done. From B to C, we do positive work by the gas or negative work on the gas, and same thing with D to A. So I should give these subscripts, right? This is the pressure at BC and the delta V BC. So this is minus P dA delta V dA. And now we just need to look at the graph to get these numbers. So the pressure at BC, right, times delta V, that is 4 minus 1 V naught, right? That's that first term. Then we have a minus, the pressure dA is P naught, and we go from 1 to 4 V naught, right? So this is negative 3 times 3, or negative 9 P naught V naught. And this one is going to be a plus, right, because we have another negative in there. So we have negative 1 times negative 3, or 3 P naught V naught. And so that gives us a total of a negative 6 P naught V naught. And that's the net work done on the gas during the entire process. So that would mean that the gas does a net work on things that are external to it, the piston that it's attached to, whatever that might be. And as long as you get it's negative, you're getting some of the points right there. So the sort of the concept recognition is a substantial fraction of the total points, just getting the fact that it has to be a negative work done on the gas. Okay? That's it.